Okay, let's look at a sequence like this one. Let's suppose that we've got a sequence is -1 to the n over n factorial. And we want to determine if that thing converges. And if it does converge, what is its limit? Well, I think you could probably figure out, yeah, I bet that limit is going to be 0. If we let n go to infinity, you've got just a number up top and the bottom is blowing up. But I want to use this as a vehicle to illustrate the squeeze theorem in the context of sequences. Now, first of all, I want to consider this n factorial, and I want to look at some values for n factorial. So let's do this. Let's look at some values for n, and I'm going to look at n factorial here. And let me just do 2 to the n. Let me compare it to 2 to the n. In other words, I've got this factorial, and then I've got this exponential thing down here. And I'm going to put in some values for n. 1, 2, 3, 4, 5. And let's just take a look at these and let's compare them. Let's compare the value of n factorial and 2 to the n. Well, n factorial, that's 1. 2 to the 1 is 2, right? Okay. Now, if I put in a 2, that's 2. This is 4. Okay. Then if I put in a 3, I get 3 factorial. That's going to be 3 times 2. And of course, this is going to be 9. And let's put in a 4. So this is 4 times 3 times 2. And down here, this is going to be 2 times 2 times 2 times 2. Okay. So it looks like the n factorial there looks like it's bigger in this case, right? Because this is 16 and this is 24. Now, if you go up here, you got 5 times 4 times 3 times 2 times 1. And down here you have 2 times 2 times 2 times 2 times 2, 2 to the fifth. And you can see that clearly the n factorial is going to be bigger than the 2 to the n from now on. Because look, you can compare these. The 5 is bigger than the 2, the 4 is bigger than the 2, the 3 is bigger than the 2, the 2 and the 2 are the same. So you can see that the factorial is going to be bigger than the exponential from then on, right? Well, that means that 1 over n factorial is, remember n factorial is bigger, is going to be less than 1 over 2 to the n for large values for n, all right, as n goes to infinity. So 1 over n factorial is less than 1 over 2 to the n because the n factorial is bigger. So it being on the bottom will make the whole fraction smaller. So we have this situation. Now, remember here we have an alternating series. So we could say this. We could say -1 to the n over n factorial. That's going to be less than 1 over 2 to the n on the positive side, but some of these numbers are negative. -1 over -1 to the n over n factorial. So on the top, you're going to have this 1 over 2 to the n, and on the bottom, you could have -1 over 2 to the n. So it's pretty easy to see that -1 to the n over n factorial is going to be between 1 over 2 to the n and -1 over 2 to the n as n goes to infinity. Now, here's what we can find from this. Since this is true, since this relationship is true, we can talk about the limit of 1 over 2 to the x. Okay, so we can just talk about the limit of 1 over 2 to the x, and you can show that that's 0. And also the limit of -1 over 2 to the x is 0. Well, that being the case, so this limit here is 0, and this limit is 0, and this is in between. So what you have is a situation where you have this -1 over -1 to the n over n factorial is being boxed in between -1 over 2 to the n and 1 over 2 to the n. So let's look at the graph of that. So here's what I've got. I've got a of x is 1 over 2 to the x. That's this red right here. And then b of x is negative 1 over 2 to the x. That's this blue right here. So I just left it continuous. I didn't just put the sequences. I just put the continuous functions there. Now I've got here uh, something that will generate ordered pairs. So I've got n and negative 1 to the n over n factorial. So you can see right now that value is at n is 3 and this is negative 0.1667. But now notice as I start incrementing it. So I've got n is 3. Now let's look at n is 4. And you can see that now this sequence here is only generating values between the blue and the red. In other words, the 1 over 2 to the x and the negative 1 over 2 to the x. So if I look at another value, there's where n is 5. And you can see that it's forevermore going to be between these two. See? So if I go to the next one, see, it's between there. Now, the limit of these two functions here is going to be 0. So if the function that's bigger, okay, so in other words, if this thing right here, if that limit is 0 and this limit is 0 and this is always between, then that must mean that limit is also 0. Now that's an illustration of the squeeze theorem. And what you have to do to use the squeeze theorem is you just have to find a function that's always bigger than your function. So we had negative 1 to the n over n factorial. And I just need to find a sequence that's always bigger than this. And then I need to find one that's always smaller. And then if you can show that the one that's always smaller and the one that's always bigger converge to the same thing, they have the same limit, then the thing that's in the middle, which is this, must also be that same limit.